Today we're going to talk about mass and weight, and then talk about motion and force, and we'll see how far we get. We may get into talking about Newton's laws, or we may say just kind of see where we end up in a half an hour. So mass and weight, we've used both of those terms quite a bit in the last week or so. But what is the difference between the two? Right? Because oftentimes when I've been talking about stuff, I use them interchangeably. In other words, I might say mass, but I mean weight, or I might say weight, but I mean mass. And often they mean virtually the same. But there is a difference, right? And the difference is this, right? So you ignore the first chunk of this, right? The acceleration due to gravity. That's just the 9.8 meters per second squared. That's how that's basically the how much gravitational pull we're subjected to on Earth. Okay. So again, taking that out of it, just think of mass as purely the amount of matter in an object. Okay. Whereas weight is measuring the pull of gravity on an object. So the way to think about that is, if you were to go onto the moon, right, and stand on a scale, gravity is much less on the moon. In other words, the acceleration due to gravity is less. So if you see up here in the formula, weight is equal to mass times acceleration of gravity. So that's where when you step on a scale and that weight comes from. You're essentially, part of your weight factored into, or your weight is factored, the mass and the gravitational pull, both factors when it comes to it. But if you were to go onto the moon and you stand on a scale, it's not going to say the same thing it says on Earth. It's going to say much, much less. You weigh a lot less on the moon than you would on Earth, just because the gravitational pull is less. But would you be physically smaller? Would you have less mass? No, you'd be the same person and the same amount of matter. You're made up of the same amount of matter. You don't get smaller just because you're on the moon. You get lighter because the gravity is pulling you down less, but your mass is the same. So mass is just how much of something there is, not taking into account gravity. That's the only difference. But last week, this week, and even going forward, I'll still use mass and weight interchangeably because they're, for your purposes, it's fine to just use them. Okay. So with that said, let's go to this next slide, and I'll try to sort through this kind of as clearly as possible, and again with minimal visual aids. In this kind of, I may even see how ambitious I'm feeling and try out the whiteboard. I've been avoiding using it for whatever reason. All right, so let's start from the top here. So a couple things first. Some of this stuff will be pretty confusing, so if some of it goes past, over your head, that's okay. There's only a few main things I want to do. But when we are talking about physics, in other words, the laws of motion, we have what we call scalar and vector quantities. Scalar quantities are only related to distance, whereas vector quantities factor in distance and direction. That's going to come into play when we talk about speed and velocity, because similarly to mass and weight, the way I use those interchangeably and how they're very similar, speed and velocity are also very similar with one minor exception. Okay. So when we're looking at speed, speed is a scalar quantity. In other words, it's only dictated by direction. And what I mean by that is, if you get in a car and you drive west 55 miles an hour, and someone else gets in a car and drives east 55 miles per hour, both of those cars are traveling the same speed. The speed is the same. The direction isn't important, right? When you're measuring speed, you're not saying, well, you're going 55 miles an hour west, or you're going, and that's not how we typically describe or use speed, right, when we're talking. But velocity, on the other hand, is dependent on both distance and direction. So velocity would be a vector quantity. In other words, when we take into account those two different cars driving 55 miles an hour in different directions, their velocities are they're opposite, essentially. Right? And the reason that's sometimes helpful in science is because sometimes the end result is important, right? So in other words, if you were to drive for an hour, 55 miles an hour in this direction, someone else drives the same amount of time, the same speed in this direction, end up in two totally different places. So in some ways, direction is important, right? Because you end up somewhere different. If you're trying to get to Seattle, you drive 4 hours going east, you're going to end up way off your mark, right? So direction is important and is factored in when we use velocity, when we talk about whereas it isn't. So what is speed, right? Everyone has heard probably both of these, speed and velocity. For sure, speed, right? When we talk about speed, we're talking about how fast something's going. But what does that really mean? Because at its core, speed is a measurement, right? It's a specific, we use the term generally and broadly, but as it relates to science, speed is specific to a certain formula. In other words, we calculate speed one way. And that is, as you can see there, distance divided by time. That's going to give you the speed that something is traveling. Okay? So, for example, and I guess, like I said, we'll just keep the math very simple. So, look down at the bottom, right? If we travel, not the bottom, but look underneath down here, underneath the formula where it says travel 12 miles in 3 hours. So let's say that's more like foot speed, right? So we're on a hike and we're hiking 12 miles. We got to make it 12 miles. You make it to your destination, 12 miles, in 3 hours. That means your average speed is 4 miles an hour. Okay? So that doesn't mean that you are always traveling at 4 miles an hour. Okay? So when we talk about speed, there are a couple of distinctions I want to make. First is the difference between average speed and instantaneous speed. So in this example here, if you're traveling 12 miles in 3 hours, you're averaging 4 miles an hour. But chances are you stop for a break, and at that time you're going, you're not moving. You're going 0 miles an hour. Maybe sometimes you're jogging or running, and so you're going 8, 9, 10 miles an hour, right? Maybe most of the time, maybe you are actually moving 4 miles. The point is, when we look at it over the course of the amount of time, right, then it essentially averages out to 4 miles an hour. Whereas instantaneous speed is how fast are you going right now, right? So if you were to drive from here to Seattle and your average speed was 70 miles an hour, that doesn't mean you're going 70 miles an hour for every second of that drive, right? Obviously, there are times when you get stuck at a stoplight, or you're getting on the freeway, or you're getting off the freeway, someone cuts you off, or your speed, right? There's lots of varying levels of how fast you're going. But when we look at it over the course of the time it took you to get there, right, your average speed, let's say, was 70 miles an hour. Right? So, whereas instantaneous speed is, you look down at your speedometer, how fast are you going right this minute, right, or right this second? So let's say you look down and you're going 75 miles an hour. That's your instantaneous speed. In other words, if you were to continue that, speed for an hour, you'd go 75 miles. That's literally what miles per hour means, right? Miles per hour is how we calculate speed in the United States typically. But think about what miles per hour means. Miles is the form of distance. Per hour, hour is our form of time. So miles per hour is just miles divided by the hours. That's what it means. But again, if we consider velocity, velocity is calculated the same exact way, except for it factors in directions. Sometimes, again, when we're talking about science, we need to make sure we account for direction, and that's when we need to talk about velocity. So if two things were going to have the same velocity, that means imagine you're on that freeway driving to Seattle. You're going 75 miles an hour. Someone pulls up to you. They're right next to you in the same lane, going 75 miles an hour. You two are traveling at the same speed and the same velocity. Right? But if that person gets off at the next exit and continues going 75 miles an hour, but now they're going off this direction, now you two have essentially changed velocities from each other. So again, that's speed and velocity. Hope that kind of makes sense. I don't want to over explain it. Let me back up 1 second. Before I talk about Newton's laws, the last thing I want to talk about, and maybe now this is going to force me to, might be scary, so bear with me. This might force me to use the old whiteboard. So the last thing I want to talk about is acceleration. So how is acceleration different than speed? So what acceleration is measuring, right, is your rate of increasing or decreasing in speed. Okay? So let's see here. I'm going to draw a nice looking car. Here's my car. Okay. I'm just going to draw really bad so Sean feels good about himself. So there's our car. So let's say we are at this point right here. We are going 0 miles an hour. We're stopped, right? So you know, cars are always measured in, or when we talk about acceleration of cars, you hear how fast they go from 0 to 60 miles an hour. So let's say right here, we're going 0 miles an hour. We're not moving, okay? Now, over here is when our car hits 60 miles an hour. All right, look at this art. So boom, our car starts 60 miles an hour. So I have no idea what is fast and what isn't. I'm just going to make something up. Let's say it took our car 4.3, woo, man, that's a 3, 4.3 seconds to go from 0 to 60 miles an hour. So how do we measure how fast that car is accelerating? So the formula for acceleration, we take the difference between our speeds at the end and at the beginning, and we divide it by the time. So that looks a little bit like probably could just type this in. Just because I'm stubborn. So that's a t down there. So the formula for acceleration is the velocity at the end of the time subtracted by the velocity at the beginning divided by the time. So if this were the case, now I'm gonna. So if our velocity at the end is 60 miles an hour, right? 60 miles an hour minus 0 is obviously 60, right? Then, if we want to find the rate of acceleration, we take 60 and we divide it by 4.3. So if we do that, which if you have a calculator, go ahead and see what you get. If not, I'll do it for us. 60 divided by 4.3 comes out to 13.95. And so what is that measuring exactly? It is measuring, so on the top, again, we have miles per hour. So 13.95 would actually be miles per hour per second. That's what that essentially would be measured. So what does that mean, right? Like we got that number, great. What is it telling us? It's telling us that on average, our car is accelerating roughly 14 miles an hour every second. 2001, 14 miles an hour. 2002, miles an hour, right? So that's the rate of acceleration. So we can also calculate, and again, I'm going to try to go through this quicker as opposed to slower. I'm not going to do a ton of examples, but we can also do this same thing. Well, imagine, all right. Now let's do bear with me here, but let's do a couple more examples. So let's say we're going 45 miles an hour. I want to give a little more complicated question. So here we're going 45 miles per hour. Then let's say we get on the on-ramp and we get on the freeway. Let me erase this messy 60. And let's say we're on the freeway and maybe we're speeding a little bit. Maybe we're going 78. Not endorsing speeding, but for the sake of this example. So let's calculate our acceleration here, because this is a little bit different. We're starting at a point where we're moving. So we're not going from stopped to 60 miles an hour. Here we're going from 45 miles an hour, right? We're moving. Now we step on the gas and we accelerate, we speed up, right? And now all of a sudden we're going 78 miles an hour. And let's say, for the sake of maybe giving us some easy math, let's say it takes us 5 seconds to speed up from 45 to 78. So we're not gunning it, right? But we're speeding up pretty quickly. 5 seconds. We're going 45. Now we're going 78. Let's take our nice formula over here. Velocity 2 minus velocity 1 divided by time. I actually think technically, let me edit this a little bit. I think, coming back to me a little bit, but actually, back to the, I don't know. So actually, it would be like this. Technically, the formula is velocity F minus velocity I. And I just mentioned that in case you ever see the formula, right? The F stands for final and the I stands for initial. So same thing, just they use letters instead of numbers, right? So 78 miles per hour would be our final velocity. 45 is our initial, where we start. Okay? So if we want to factor this in, or if we want to calculate our acceleration here, we do 78 miles per hour minus 5 miles per hour. What does that come out to? 78 minus 45 comes out to 33. We increased our speed by 33 miles per hour, and we divide that by 5 seconds. And we get 0.6 miles per hour per second. Right? So we're increasing 6.6 miles per hour every second. Right? I think that's straightforward enough. I don't need to spend a whole lot more time on it. The last thing with acceleration I'll talk about is, can you have a negative rate of acceleration? Can you negatively accelerate? What do you think? Usually I ask this in class and the results are mixed. Some people say, no, you can't. Some people say, yes, you can. But when we're talking about acceleration doesn't always mean positive. You can have a negative rate of acceleration. If accelerating means to speed up, then a negative rate of acceleration is just a fancy way of saying you're slowing down, right? Or you're decelerating. So if I was to give another example, let's say you're on the freeway, no one's around, you're cruising now, you're going 80. Let's say a deer pops out or a cop, you see a cop or whatever the case may be. Let's say for whatever reason you have to slow it down to 55 miles per hour. And let's say that you really crank on slam on the brakes and you go from 80 to 55 in 2.3 seconds. So go down here, formula, and we would do the final velocity minus the initial velocity. So even though the 55 is smaller, we still do 55 miles per hour because it's our velocity or speed at the end of the time. 55 minus 80. And if we do 55 minus 80, we get negative 25. Negative 25 divided by 2.3 out to negative 10 point, rounded up to 10.9 miles per hour per second. So that means we're slowing down. A negative acceleration just means you're slowing down almost 11 miles per hour per second. Again, I think we have an idea of speed, acceleration. That's kind of all I want you to take away. Let's see, 137. Let's see how much of Newton's laws we get to, and I think we'll save practice questions for another day. I'm about practice questions, and I don't want to for you. Let's just kind of talk about a few more things, and then we'll. So let me stop this here. Go back to my old one. All right, so hopefully everyone can see PowerPoint, and let's go and run through real quickly the biggest thing when it comes to let's go back to talking about Newton's laws. So Isaac Newton, maybe you've heard of him. 3 laws, right? Main 3 laws that kind of govern physics, right? The first law, Newton's first law, an object at rest tends to stay at rest. An object in motion tends to stay in motion in a straight line at a constant speed. Okay, so let's stop there. And also, it probably should read at the very end there that they tend to stay in motion in a straight line at a constant speed unless acted upon by an unbalanced. We'll get there. So kind of a confusing way of something very easy to understand. Okay, let's break it down into 2 parts. First, an object at rest tends to stay at rest. What does that mean? That means if I set this calculator down, right, if I set it down, right here, imagine this is sitting on the table. This calculator isn't going to move on its own. It's not going to get up and jump off the table. It's not going to fall off the table without something adding a force to it, right? In other words, it's not going to change unless I pick it up and move it, or something shakes and it falls off, right? So that's the unbalanced force. The reason that Newton uses the term unbalanced is because if we apply a balanced force, something that means we're applying equal force from every direction, right? And if you put an equal force on something, if I push on this calculator with both hands, it stays still. But if I push harder with one hand or the other, then it moves, right? So that's why he specifies by saying it has to be an unbalanced force, okay? So first thing, object at rest. So an object that's not moving isn't going to move on its own, okay? Now let's look at the other part of that. An object in motion tends to stay in motion in a straight line at a constant speed. So if I throw this calculator at my computer, right, it's going to stay moving. In other words, it's not going to stop in midair, right? Stay moving, and it's going to go in a straight line, a constant line, or a straight line, and it's going to go at a constant speed. In other words, it's not going to slow down or speed up. It's just going to go straight at the whatever speed it is that however much force I put on it, it's going to go at that speed, and it's going to go that way forever. So when I throw my calculator out the window, why doesn't it go forever? And the easy answer to that is gravity. Gravity in this situation would be unbalanced force. That's ultimately stopping or changing direction or changing speed of my calculator. If I was in outer space where there's no gravity and I threw this calculator, it would go in a straight line at the same speed forever until it either hit something or got pulled into something else's gravitational pull, right? But if it was just an empty space, this thing would go straight line, same speed forever. Okay? So that's the second part of this. The object in motion will stay in motion in a straight line at a constant speed, acted upon by an unbalanced. Right? So if I throw this at my computer screen, the reason it's not going to go forever is it's going to hit the computer and fall, right? That's going to be the unbalanced force stopping it. All right, so let's look at Newton's second, up against the clock. And if I have to stop short and revisit this, then that's okay. Okay, so Newton's second is not quite as straightforward. It says if an object has more inertia than another, more force is required to give that object the same acceleration. Okay, so kind of confusing. Well, let's try to break it down because it's not as confusing as. Basically, the second law describes this formula for force. Force equals mass times acceleration. In other words, how fast something is accelerating multiplied by how big it is going to essentially tell us how much force something. So let me think of an example. And I'll go back to my example of being hit by. Okay, so let's take my favorite examples of the calculator and the big GED, right? I'm lacking for better examples around here, so that's what I've got. So, two objects. Obviously, the book has way more mass than the calculator, right? Now, if both objects are accelerating at the same rate and they hit me, which one's going to hurt me, right? The book, obviously, because the book is traveling with more force. Right? But if the book is accelerating very slowly, the calculator is accelerating very quickly. It's going to hurt to get hit by the calculator. I didn't quite mean to hit myself that hard in the head. You get my point, right? So that's essentially Newton's second law. The flip side of that is that objects with more mass require more force to move. So it's the same formula, but it's looking at it a little bit different. So Newton's second law also describes, the amount of force it would take for me to move this desk is a lot greater than the amount of force it would take for me to move my chair, right? I could get up and I could push my chair very easily with very little force, right? But if I go to push my table with that same amount of force, the table doesn't go anywhere, right? I have to add more force in order to move it the same rate of acceleration. Does that kind of make sense? Let's go over Newton's third law and then we'll stop there. Newton's third law is probably the one everyone's most familiar with. For every action, there is an equal and opposite reaction. Right? It's down there, for every action force, there is an equal and opposite reaction. You've probably heard it just, for every action, there's an equal and opposite reaction. What does that mean when we're talking about physics? That means literally what it sounds like. For every action, there is a reaction moving in the opposite direction. So the kind of the best example I can give of Newton's third law would be if I was, I can't get up and move around, but if I was right here, so you can still see, I'm pushing against this door. I'm adding force. Hopefully you can still hear me. I might have to talk a little bit louder. But if I'm adding force to the door, I'm pushing it in this direction, right? The door is pushing back against me equally in the opposite direction. Why am I not moving? Well, imagine if I'm on a skateboard, right? So now I'm on a skateboard. What happens if I push against the wall this way? The wall pushes me back in the opposite direction. If I push this way, I don't move this way. I move the opposite direction. That's Newton's third law. Okay? Now, it also says equal and opposite. So the opposite part is if I push against the wall in this direction, the wall pushes me back in this direction. But it also says equal. So if I barely push against the wall and I'm on my imaginary skateboard, right? If I tap the wall, I might move just a little. I'm not going to go flying back against the other wall. If I push really hard, I'm going to go flying back this way, right? So the amount of reaction is always going to be equal to the initial action. Okay? So the last example of this is like how rockets work. So the thrusters on a rocket are on the bottom, and they point down to the ground. They don't point up, right? They point down. And when they fire up, they're exerting a huge amount of force down to the Earth. The Earth is then taking that force and sending it back to the rocket equally, but in the opposite direction, and the rocket shoots up. Okay? So that was a little bit quicker than I wanted to go over Newton's laws. So we have more questions on it. We might go over some of it on Monday, but I don't want to run over too late. So let's stop there, and hopefully that made some amount of sense for everybody, and that was okay with the limited amount of visual aids I could do. But that is Newton's laws and motion and force kind of in 30 minutes.